Okay, how's that? Let's try it. Okay, so not said it's muted, so that should work. Okay.
Okay.
All right, so we can get started. So we're happy to have Lorenzo Mansi speaking about orthosymplectic decay and fusion of magnetic quivers.
So thank you very much for having me here and having given me this opportunity to give this talk. And so yeah, today I'm going to discuss about this decay and fission of magnetic quiver. So hopefully we will manage to explain all the words that are in this title. We'll see how it is. So first, let me start saying that since this is a seminar both for physicists and mathematicians, I'll try to bridge like the two subjects together and kind of like give a dictionary of what we mean in each of the two settings. So the main idea here is to consider what we call 3D N=4 Quiver gauge theories. So the main idea is that all of you, like being a mathematician or physicist, have heard people talking about that, and I think quite a lot. The main point that I want to stress is that when as physicists think about this theory, so what do we mean by giving a physical theories and then some fields in the theory? The idea is that this theory being in 3D as an isometry group that's given by the Poincaré group in 3D. And what do we mean by supersymmetry? Essentially, we do a Z2 grading of this algebra and introduce what we call like fermionic operator, and this will give us like what's called the supersymmetric Poincaré algebra, so super Poincaré. And we will regard the fields and like in our theories as a representation of this super Poincaré algebra. Now, one thing that's extremely important is that this algebra admits an automorphism that actually keeps the Poincaré part invariant and only permutes this fermionic field that we added with the Z2 grading. And this is something that we call the R symmetry. In particular, for 3D N=4 Quiver gauge theories, this R symmetry is actually like the R symmetry algebra is a direct sum of two factors. Like one SU2 acting on what we call the X branch and SU2 acting on what we call the Coulomb branch. Now, what are these two? Actually, as I was mentioning, one of the things that we're particularly interested to know about these 3D N=4 theories is what we call the moduli space of vacuum. So you should think of it in this way. We can take like the first representation that we have here, which is the hypermultiplet. This hypermultiplet is inside of it contains some scalars, so things that transform trivially under this Poincaré group, and then give what we call a vacuum expectation value to them. This is what defines the X branch modular space. So this X branch is actually a variety that is classical. So it doesn't receive what we physicists call quantum correction, and more importantly, it emits an hyperplanar structure. So
the Higgs branch doesn't have quantum correction.
No.
Though the quantum correction for Coulomb branch has to do with the matter, the choice of matter.
Exactly. So I'll explain it.
And here we have still a choice of matter, but you call it all classic. Okay.
Yeah, the difference between classical and quantum for us is like this. So when I give you a Lagrangian, suppose like in physical terms, I put some terms of this for. So 1/2 d mu phi plus m phi squared. So I have this mass term.
Yeah.
This is a number that you put in your theorem. That's fine. That's what we call the classical mass. Then, if we start adding Bose interaction, like by Feynman diagram, we can compute like what's called loops in the diagram.
Yeah.
And so these loops actually change the value of this mass. And so this is what we call like having a quantum correction on our theory. So the number that you put here, like writing the Lagrange, actually receives contribution at later order when we construct these loops. So the important thing is that here in the X branch, like this effect of considering higher loops doesn't take effect. So
What are these symbols you put under the SU2s again?
X and Coulomb, just to remind me that this SU2 acts here, whereas this SU2 acts on the Coulomb branch that I'm gonna write here.
Okay.
So
This is a subgroup of super Poincare.
this is an external automorphism of the super Poincare algebra
External.
that keeps the Poincare part invariant and acts only on the new operator that they introduced with the Z2 grade.
You mean it acts trivially on the Poincare part?
Yeah. Okay. And produce the other. So this hyperciliar structure actually as this space can actually be constructed mathematically in a fairly determined way. So if I give you a gauge theory with some gauge group G and then a flavor symmetry, you can write down a moment map for this flavor symmetry and then just do what's called like the symplectic quotient by the group G. So this is mathematically well defined. We have it under control. We are very happy with it. But what about then this other side? So this other side is what's called the Coulomb branch. So here I was saying that the main parameters of this space are the scalars in the hypermath. So these are two complex scalars, phi1 and phi2. Whereas here we have one real scalar and a vector field. So what do I mean by this? So I'm giving you a G bundle and a section of the G bundle. And the value that this scalar field acquires, like parameterize my Coulomb branch. The Coulomb branch, differently from the X branch, actually receives quantum correction. So it's something that if I write them classically, then I know that this space will receive some changes. And the question is, like, do we have some mathematical structure to interpret it and have it under control? The answer is that this is very difficult to define, so very difficult. But what is the beauty of 3D unequal for Quiver gauge theory? Is that both of these spaces actually are symplectic singularities. So
the quantum means this extra loop corrections to the math.
Exactly. That was
But when you have the quiver, the dimensions, etc., those are just these extra corrections.
Exactly. So,
but on the Higgs side, they're not.
So I'm gonna skip over and tell you what's the quantum correction in this side. So in the Coulomb branch, like the idea is that instead of parameterizing it with the scalar fields, what we do is using monopole operators. So when this actually, let's do something. If you wait 2 minutes, I'm gonna tell you the answer to the quantum correction. Where do they arise in the Coulomb branch? Because I'm gonna explain like what a Coulomb branch is for us physicists, and how we describe it, and then that should set all the doubts apart. If you still have doubts, then please continue asking questions. So what I just wanted to say is that both of these spaces are symplectic singularities, and so symplectic singularities.
Maybe depending on what your assumptions are.
Yeah, exactly. So now I'm giving you like what I mean by symplectic singularity. I mean a variety, an algebraic variety over C X, such that X should be the normal Poisson.
But the Higgs branches are not always that form.
Generally, yeah, but I'm going to just focus on this kind of varieties. So second, I will require that there exists an open subset inside of X where this Poisson structure actually comes from a symplectic structure that I will call omega. And moreover, it must exist a resolution of this singularity X such that the pullback of this symplectic structure has no poles. No poles on X theta. Now, generically, like for symplectic singularities, we like as physicists mean something more. So we just mean conical symplectic singularities. Conical just adds like two further assumption that X is affine, and moreover that there exists an action that contracts a sister action that contracts our variety to a singular point. Now, why do we say that we want the singularity to be conical? The reason is that this requirement turns out to be equivalent to our theory being good in a physicist sense. So in reality, like for us, we can treat also non-conical singularities, but the idea is that the way that we understand them is by zooming near each singular point and treat them as conical. So we don't have a comprehensive understanding of them. We can just zoom in one singular point, isolate it, and understand it that way. So why am I mentioning this? Because, well, in maths, it's well known that there exists a phenomenon known as symplectic duality that relates to symplectic spaces. And this is the same of what as physicists called 3D mirror symmetry. So, and this is the same of symplectic duality. So, what we have is that given an X branch of a theory, which is classical, I can compute and understand it completely, I can then use this 3D mirror symmetry to engineer a theory whose Coulomb branch, resound with all the quantum correction, it's equal to the X branch of another theory. So these two theories form a symplectic dual pair.
I think symplectic duality really is supposed to have just concerning the relationship between these two symplectic singularities.
Exactly.
It doesn't have to do with the theories, whereas I guess
But
the 3D
for us,
mirror
is
symmetry has to do with the theories as well. Right?
It has to do.
Symplectic duality, I think, is just about the symplectic singularity,
Yes,
the
with
mathematical relationship.
this one, and this.
Whereas the 3D mirror symmetry, I think, has to also do with the theories, right? You have like two different theories which switch the Higgs and Coulomb branch, right?
Yes. I mean, obviously the symplectic singularity, the symplectic duality part only looks at the two branches.
Right.
Whereas when I make the statement about the theories, I'm making a bigger statement.
Exactly.
So, but for what pertains to this talk, I mean, you can assume that they work in the same way. Like just to get an understanding of what I'm discussing and what.
So you're just
what the
interested in the
message
Higgs and Coulomb branch of a particular theory. You're not going to talk about.
exactly.
a
I'm not
mirror
going to
theory.
talk about the
Okay.
mirror theory.
All right.
That's what I want to do. And that's the reason as for why I'm mentioning like this word magnetic exactly means that I'm just focusing on one theory.
Oh, I see.
I'm
You
talking
don't
about-
care about the electric quiver. You only care about the magnetic one. Okay.
So having said that, I still need to tell you why do I care about symplectic singularity, like at least for my research. Well, there's a theorem due to Kalindin that states that given symplectic singularity X, there exists a stratification Xi inside of X in like by Poisson subscripts. And this stratification is what we call a foliation. And so each one of these leaves, actually the closure of this leaf, is a symplectic singularity in itself. But moreover, if I take any point X inside the open part of one of the leaf Xi, then the formal completion of this point X inside of my variety is actually equal to another variety Y, which actually is Poisson by itself times the formal completion of the point x inside of the open part of the xi. So what I want to do is actually study then the foliation of this symplectic singularity, determine which are the leaves that constitute it, and stratify it completely. This is something that for us physicists, like we'll just refer it to as a X mechanism in this particular context. So the idea is that I want to use symplectic singularity and Coulomb branches as a portal to understand the foliation of the symplectic singularity. And to do that, I want to use quivers. Moreover, I want to use like quiver algorithms. So I just want to take a quiver, do some operation on top of it, and associate a quiver to a symplectic singularity, and then another quiver to one of the strata in the foliation of the singularity. So in order to do that, I need to tell you what a Coulomb branch is. So to do this, let's start from the physics understanding, and then we do like a little brief sketch of what's the math understanding of a Coulomb branch. The main idea is that I start, as I was saying, with the representation of superpointary algebra. In particular, I take what I call like the vector multiplet. So this vector multiplet comprises a real scalar, then complex scalar, and then a gauge field. So, as I was saying, G bundle and section on the G bundle. Then what I want to, what happens is that if the scalar acquires a non-trivial value, then the gauge group that I chosen to be G in a generic point is broken to its maximal torus. So generic. The way that we manage to understand what's going on in the Coulomb branch in general is by resorting to monopole operators. So what do I mean by this? When a physical theory is given, what I'm actually giving you is a partition function. So this is just a formal integral over all the fields in my theory to E minus the action of the theory. So when I insert
I don't understand this generic thing.
generic point,
Generic point.
yeah.
G is the group you're using, the gauge
Yes,
group.
I'm giving you a gauge theory with gauge group G.
Right.
This means that in representation of the superpointary algebra, together with the G bundle, I'm also giving you some section. In
Right.
particular, like this guy here.
But what's this thing, generic point? I still don't understand.
These points, now I take the scalars to
Yeah.
be the parameter of my manifold.
Yeah.
And I want to know what happens to the gauge group G when I give some values to this guy in general. So if I give a particular value that I don't tune it, I give whichever number, then automatically the gauge group G is broken to the maximal torus.
Okay.
So in a way that maybe it's a little bit more.
There's not a map from G to U.
No, it's not. It's not a map. It's not a map.
It's just that when you put on some parameters, then you only have this subgroup acting.
Exactly.
U2 rank G sitting inside of G. U of one. Is that U of one?
U1. Yes, it's a U1.
Okay. Sitting inside. Okay, it's a subgroup. Okay. All right.
So the idea is that you insert a monopole operator, which is a thing that I call an X. That means I pick a point X in my space, and then here I assign a singularity for this gauge field. So the behavior is something like A goes to plus or minus 1 plus cos theta, where I'm using the radar coordinates around this point. And so I have a north patch and a south patch. And since this thing must be single valued along the intersection, then I need to require that X of I by M, it's equal to 1. So this condition here, it's a quantization condition because it's telling me that I cannot pick M however I want, but M must sit, and this we'll write it down here because something that we need to keep in mind, must sit inside the weight lattice of the GNO dual of the gauge group G that I pick. But another thing is important. So for us, species symmetries come in two pairs. So gauge symmetries and flavor symmetries. When we have gauge symmetries, we want to identify everything under the symmetries. Whereas when we have a flavor symmetries, like we have different objects that are then acted upon a symmetry. In this case, this thing is a gauge symmetry. So we need to model it out by the Weyl group, so that we're sure that this thing is invariant. Now, you should ask me, well, I gave you like 3 different objects. So I'm now specifying something for this A. What happens to these other fields over here? So what's going to happen is that supersymmetry imposes a behavior also for the field sigma, which will go like M over 2R. But then now we come in play with the point of quantum correction. We have yet another field that we need to think about, which is this complex scatter. I have 2 possible choices. Either I put it to 0, and this is what I call the bare monopole. Or there is another option that I can take, which is I can take, if I turn on this M, there will be a commutant inside of G of this M that will survive, that will happen. And so I can turn in HM, where HM is the commutant inside of G.
The centralizer? Or
Yes, the centralizer.
Okay.
Okay.
I'm still not following. What is it? Why did M arise here? What is this VM of X coming
So
from?
this is the monopole operator that I'm constructing.
You're constructing a monopole operator for every weight.
Exactly.
Why?
So the thing is that if I construct like the monopole operator in normal gauge theory, it's just given by giving a singularity to this guy.
Giving a singularity.
So this one, like if this point is X, goes to 1 when R minus X. Like there is a delta. Thing is, if I assign this value for this guy, now I need to ask myself, I'm working with the representation of a superpointary algebra. Does this value that I assign here, is it this value compatible with my theory? So with my Lagrangian, I want to preserve supersymmetry. I want to stay in 3D unequal form.
What is A here?
Is this?
That A sub U? Is it a U?
Yeah, it's I put an index notation here. This is just the connection on a principal G bundle.
So A is a connection.
Yes.
So now you're writing a formula that just involves a single variable. That's phi here.
These are coordinates around this point. I'm in 3D. So this is the theta component. This one, theta. This one is the.
A is a connection on a principal G bundle.
Yeah.
I don't see any G involved here. It seems like a
This is just the fact that I'm assigning the behavior next to the point, but this A is valued in the adjoint representation of G.
But it doesn't look like it when you write it this way.
Yeah, this is the, I mean, yeah, you're right. So let's fix this. So if I put like my generator for the group G, the joint representation, I label them with A, then you would have A, but you would also have a dependence on the space coordinates. And this is this mu over here. And so this part is the spatial part, and this is the group part.
So for every index, A is indexing a basis for your Lie algebra or
Yes,
something?
yes.
Okay, little a that is. And what's the relationship of these monopole operator to this integral?
So
This is
the,
action.
the thing, yes, this is an action. So what I'm writing down here is that you can insert operator in the action.
Into the action.
So you can put them here.
All right.
So since this one is singular at x, then also this integral will become
But if you
singular.
insert the this operator using this weight, then somehow this restricts that your
The fact
complex
that I
scalar.
want to retain supersymmetry
Mhm.
obliges me to take some kind of behavior also for the other things that appear in this multiplet. Because all of this block is a representation of superpoint array. It's not only this guy. So if I assign something for this, then I need to see, is this compatible with also the other elements that I have? And the answer is that yes, but you need to pick specific things. So you can pick, you need to pick this profile for the scalar field. And for the complex one, instead, you can either put it to 0, and this will give you the bare monopole, or you can give it a value, because this is an adjoint field instead of Lie algebra. So also here I should put an A index that lives inside of the commutant of M in G.
So this parameter A is just this vacuum or this this monopole operator for the little m. The big A is only using this little m somehow concentrated at this weight. Little m, and now you need to be a representation of superpoint array. The complex scalar has to be in the commutant of the in the the centralizer of this.
Yeah. If I want like the rest monopole, yes, this is better and this is the rest. So the idea is that from these things, I want to construct some ring of holomorphic function. I'm gonna give a grading to this ring of holomorphic function. And once I've done this, I can write down an inverse series. And my Coulomb branch would just be the spectator variety of this of this ring of function that I want to do. Like physics, like the way that we think in physics is like this. So we have this thing that well defined for every gauge group. And you can define then the monopole for every gauge group, because you can see that here I've yet to talk about Quiver. So once I do this, then where is the matter part that comes that you told me, yes, but we also have matter in the Coulomb branch. So the fact is that when I assign the grading now for this function, I assign grading according to subset. Remember that I told you that there was this external automorphism, these SU2 factors. I pick a specific combination of these two that gives me a U1, and then I assign weights under this U1. And the assignment of weights under this specific U1 is that these guys here come with weight 1, whereas the matter, that's another representation of the superpoint algebra, which is the hypermultiplet with two fields. This one will have weight 1/2. So when I write down the monopole formula and I'm assigning the charge, now we'll have a charge for the bare monopole, this guy. We'll have a charge that's given by minus the sum over the simple root of my gauge group, M plus, now here is the contribution of matter. The 1/2, the 1/2 charge that's assigned here, 1/2 sum over all the matter fields that I have in all the representation that they come. So, of M. And where is the quantum correction part written? In the fact that if I write down an inverse series, so now I'm counting operators according to this charge. So I have a sum over M, because M was what I'm counting. Now I'm counting monopole operators. T to the delta. And here, there is a classical factor that counts the gauge invariant of the group HM that I've written before. So this is counting the degrees of the Casimir invariant of HM. And this is the part that if you expand it, see, this will look like some like 1 over 1 minus t. If I expand this, 1 plus t, blah, 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 it multiplies this guy. So it's actually changing the exponent. So these are the quantum correction. However, resumming the quantum correction. So if the variety is classical, I can write down immediately as an example, like I take, we take this, take C of X, then you know that at degree 0, you just have 1. At degree 1, you just have X. At degree 2, you have X squared. And so on. So you can write down automatically the inverse series for this variety as 1 plus t squared plus blah, blah, blah. Here, what I'm telling you is that if you try to do this with the variables that I've given you in the beginning, so this sigma, phi, and mu, so you type b, so you start writing polynomials on b. These polynomials, they have not the correct degree. The reason why is that because when what you're counting in that way would be just the configuration where this guy is 0. When this guy is not 0, then you have a shift in degree, and these are quantum corrections, and the quantum corrections are repackaged in this part.
So what are these triples supposed to represent in the beginning? These are some fields, you said. What does that have to do with operators? What do fields have to do with operators?
But there's a correspondence.
Between fields and operators.
Yes.
Every field corresponds to an operator. But the M isn't in this data, or the M is in the A.
The
A
M
depends on
now
the M.
comes when I construct this guy,
That's an operator.
which is an operator. Yes.
So it corresponds to a field, you see.
Correspond is an operator in a supersymmetric field theory. So
Mhm.
I'm assigning actually a collection of things, no? Because I'm not assigning just one field, I'm assigning 3.
Three fields that
Yeah.
correspond to the operator. So given those 3 fields, you get this operator. But the M is this element M is encoded in the A then.
Yeah, because when you pick the representation, you say, okay, you have the superconcatenate algebra, then you have the hypermultiplet representation, which is the first one, which is this 2, and then you have the vector multiplet. When you have the vector multiplet physically, then you also need to assign a gauge group. So that's where this G comes in play. So I say that I pick this, I'm picking a vector multiplet, but I also need to tell you which gauge group I'm picking.
Mhm.
It's additional piece of information. So that's where this G comes. And then since this M is an element of this G, then this is just a choice when I'm assigning operators. It's all a matter of, building upon previous choices. That's the thing.
So there's an additional choice. This M is
Yeah.
an additional choice. You start with a choice of a
Exactly.
triple like that.
You start with a choice of representation of isoconcatenate of a superconcatenate algebra,
Right.
which motivated by physics is that I want a representation that contain at most a certain value of spin, which is the eigenvalue with respect to an SU2 factor.
Mhm.
So with a certain weight. I don't want that weight to be more than something, otherwise I'm talking about gravity. And this is what I don't want to do. So I only have 2 representations where to pick from, which are the hypermultiplet and the vector multiplet representation.
The vector multiplet is a representation of this G, though.
Is that the vector multiplet, then I'm saying I need to pick a gauge group G, and this will live in an adjoint representation of the gauge group G.
But it also is a representation of the super.
But also a representation of the superconcatenate. Exactly. Then at this point you say, okay, I want to construct a monocorrelator. So we're adding another layer.
Mhm.
When you construct this, you need to specify yet another thing, which is this M, the flux. The way that you do it is that since you want something to be well defined in your context, and we're building things stepwise, no?
Mhm.
Now you need to say, okay, but I'm making all these choices. am I actually free to make them all, or am I obliged in some way? The fact that you have single valuedness over here obliges you to have M in this way. So weight lattice modulo value. And then we say, okay, but remember that I started from the Poincaré algebra. So is this compatible with what I've started with? And so you say, okay, sigma must behave like this to be compatible. And this phi must behave like this, otherwise it's not compatible anymore. It's that we're not anymore integrating.
The thing is, this HM is a vector space, right? And
Yes.
phi, I thought, was an element of the vector space. Isn't it?
Phi,
You said it was a complex scalar phi.
yeah,
So that's not a vector space.
but
it's an
this
element.
is a section on this on the G bundle that I'm assigned at the end.
Yes, but you can't set it equal to a vector space. You're saying phi
Very
equals-
sorry, element. An element of this.
The HM is a subalgebra of G, the algebra of
Yes.
G. And phi was just a complex scalar. You said it wasn't
A
an
complex
element.
scalar means that transform trivially under the Poincaré group. But then under the other group,
But that
which is
also,
the H group.
this whole triple has an action of G on it.
Exactly. And so these guys are all adjoint elements, are all adjoint value.
So it's actually not just a triple, some collection of triples. You're looking at a vector space of triples.
Exactly. You can, yes. Think of it.
You're looking at a whole vector space of possible triples like this, and for every element of this vector space, you could have some additional operators VM that are
Exactly.
compatible with it. And now you get a larger vector space, and now you want to take its Hilbert series, and you say this actually forms an algebra, and the spectrum of this algebra, for some reason, is supposed to be some moduli of vacuum states of some particular form.
So you can think of it like repackaging all the information that I'm giving you in a short way. It's like this. I give you a variety, which has some parameter, then I make a transformation of what are the parameters. So I make some redefinition of variables, and then I'm now constructing polynomials in these new variables, and this is the inverse series that I'm constructing. So I didn't change the original variety. So what I've done is a change from these triplets to the monopole operators, and
But
then
from the physical point of view, why is solutions of some equation or whatever supposed to be given by spectrum of this algebra of operators?
like your question is why is this physically working?
Why is the spectrum of this algebra that
Yes.
you're constructing, which you're not really constructing, but you're telling us about, why is the spectrum of this algebra supposed to correspond to some moduli space given by the theory? What are these operators and the algebra forming that have to do with the original? You say it's Coulomb branch of some theory.
Yes.
So why should spectrum of this be a moduli space like a Coulomb branch?
So the thing is that for us, like Coulomb or X, just depends on what are the initial bit what is the initial bit that you make here in the representation of the Poincaré algebra. So if I pick the hypermultiplet.
Okay, but
then
why
I'm
is
saying
the
these are
spectrum of this algebra moduli space for you?
Because to me, like the definition of modular space is just the set of minimal solution for some Lagrangian that I started with.
So why is a character of this algebra of operators a solution to Lagrangian?
Because
Like you haven't talked about the multiplication. Let's say we understood that we can multiply these things. So why should a solution to your Lagrangian give you a character of this algebra of operators?
well, that boils down to the fact that if I consider, for instance, let's do it like this. Let's forget this and let's go to basic physics.
You don't have to spend, you're gonna use your whole talk up if you try to teach me basic physics. It has to be something short.
So you can take only scalar theory with three scalars and write down a superpotential of the form like x, y, z. Now, my Lagrangian will be made of a kinetic part plus some part that looks like this. So you can see that the minimum of the Lagrangian sits when all these terms are zero. So when all these terms are zero, you have just 0, x z equals 0, and y z equals 0, which is a code.
Sure.
And you have various codes.
Yeah.
So how can I talk about this variety? I can just say, okay, I can take my variables x, y, z, and then I write down
X, Y. I guess we meant X, Y equals 0 at the end.
x, y, yes.
So this is going to be some.
X, y, z, and then I just quotient by the relation that I have. So it's the same construction that I wanted to do before. But the only thing is that here I'm making explicit that I have a Lagrangian and I'm minimizing it in this way. And I'm talking about this solution as this.
This is a coordinate axis.
Exactly.
This particular one. Yeah.
Exactly. And the thing is that when you have a theory like this theory is Lagrangian because you can write it down explicitly.
Yeah.
But in physics, there are some theories where you don't have the Lagrangian.
Right.
But the fact that you can construct this is still true.
Okay.
So I can say I construct this, and whatever I get, I define it.
Right. But
To
what
be-
I'm just asking, given your Lagrangian that you get from the physics for this supersymmetric gauge theory, why does it correspond to characters of this algebra of operators? That's what you're saying, right?
Yeah, like to me, that's the.
So for you, in this picture here, it's obvious that this algebra, C bracket X, Y, Z, X, Y, whatever, is the algebra of operators associated to this.
So to a theory, yes. I mean, like, to me, the thing is that once you specify like the physical content, this is called like you want to find the minimum, you want to find the vacuum. There is a one-to-one correspondence from this to writing down.
Because it was like some sort of thing where you started with some multiplets and then you added in some weights and stuff. And then when all of that was done, now you said the spectrum of this corresponds to your solution. But it seems kind of
It's like
ad hoc.
here, what I've said is that I started with 3 chiral fields. So
Yeah.
3 representation of, in this case, for the n equal 1 algebra. Then from this one, I build a superpotential.
Yeah.
Which is another layer. Then from the superpotential, I want to find the minimum, and then the minimum gives me this.
Yeah.
This is the classical procedure. And there, I'm kind of doing the same thing. So I start from the vector multiplet. Instead of constructing a superpotential, I'm saying I construct monopole operators. And then these monopole operators, while here I could write down the relation in an explicit way, here I'm saying I don't have access to relation explicitly, so I just count.
But you know what these monopole operators, etc., exactly the functions on this modular
Exactly.
space for some reason, and that I don't understand.
That's why
it's
it's
true.
the construction. The fact that you start with this, the monopole operator is just an assignment on this guy that has a singularity. I say, okay, pick this field and then I give like some singular behavior next to a point. So
Okay. Well, that's okay. I guess I'll ask more about it another time.
then in this last 10 minutes, at this point I will skip over the mathematical definition of the Coulomb branch, but the idea is just that you use a classical technique in algebraic geometry, which it's the standard thing of saying, okay, I start with some space, I want to construct an homology group on this space, a convolution product, and then I define the variety to be the spectator, this homology group given this convolution product. That's the construction that Bremerman, Finkelberg, and Nakajima give of Coulomb branches. But the way that they do it only applies to a single group G with some symplectic matter like the G is complex reductive, and then they put some matter M in a symplectic representation of G, usually of this form. And then when they define the Coulomb branch, they have no way to say, oh, G depends only on M, but actually, like the Coulomb branch depends only on M, but they have a construction only referring on N. But this for me, like it's a single piece of a quiver theory. So when I write more general quivers of this G, usually if it's here and I'm just taking the compact subgroup of UN, we write down something like UN1, UN2, where this line, like for you, just will mean that there is an homomorphism from M1 to M2 that I'm assigning, and so on. The formula that I wrote down before, which is the monopole formula, is something that was referring only to the single part plus this line. And so I'm attaching various parts. I have this part attached to this part, attached to this part, and so I can construct larger theories. But if I want now to construct the way that like a G and other people do, so with constructing a homology group, then I need to construct the homology group for all the space. I cannot glue them together. At least there is no notion, as far as I'm aware of, that allows you to do that. And so that's why, like, we use this monopole formula as physicists for general quiver theories. These allow us, like, to discuss about now the decay part. So the idea is that I have a symplectic. I start with a symplectic singularity X. This symplectic singularity that I pick, I choose it such that there exists a quiver theory of which is the Coulomb branch. So this is also the Coulomb branch of some quiver Q. Now, we said that there exists a foliation of this singularity. So suppose that something like this. Also, the closure of this leaf over here is another symplectic singularity. So I call this one X1, whereas this one. Now, my question is, can I, from just looking at quivers, to extract from a quiver Q prime, such that its Coulomb branch, it's actually the symplectic singularity associated with the X1. And I want to do this just by working on the quiver. So I just want to change some levels in the quiver and get this stratification step by step. Our first place where to investigate this is in nilpotent codes. So let's take an easy example. And suppose I consider the nilpotent cone of the algebra SU4. Now, let's see if I can 3,1 squared, 1 squared. So here I'm just saying these are the corresponding nilpotent orbits, and P1, 1, 3. Is there a quiver theory whose Coulomb branch moduli space is actually this symplectic singularity, so the cone? The answer is yes. And this theory is the following one. So this is a 4. One. And then I say, okay, but I can slice this cone however I want. Suppose that I pick this slice. Is there a quiver that gives me exactly this slice? The answer is yes. It's 4, 2. Is there a quiver that gives me exactly this slice? Yes. So it's 4, 2, 1. And then I ask myself, what did it change from here to here and from here to here? So as you can see, I kind of did the subtraction on these levels. So here I subtracted 1, 1, 1, and then I got this quiver. Same way, here I subtract only a 1 over here, and then I get this. Then this one will be easy to guess for you that this is just subtracting a 1 from here. And the thing that I want to ask you is there any way that I can give this kind of pattern some sort of control for even weird shape of quivers, such as, I don't know, I can point out something like this. 3, 2, 1, 3, 1, 3, 1. This is something that just by looking at it, you cannot associate like some known, maybe nilpotent orbit or a fungus minus, like slicing a fungus minus. Just looking at it, you know it. But is there a way that I can access whichever is the symplectic singularity associated with this Coulomb branch, just by changing numbers? The answer is yes. There is a statement that actually can be made mathematically precise of how this quiver behaves. So the statement is what follows. So we can take essentially like, let's say, yes, we can regard the quiver Q as a composite object given by an adjacency matrix A and some vector K over X. So this matrix will be a matrix n by n, where n is the number of nodes in the quiver valued in Z, and this K instead will be an n valued vector. So the way to construct the adjacency matrix for us will be the following. We will conventionally choose to have the diagonal entries corresponding to the node I will be -2 plus 2 times the number of loops with that node. So if I were to put a loop here, this would be 1, like G would be 1, and so on. And I assign like AJ, just for this torque, I'm gonna take to be geometric symmetrical and take it like this. But this can be made more general, equal to the number of lines between I and J. Now, I want to construct some kind of partial ordering that allows me to recover like this vector case, and so quiver theories. How do I do this? Well, very briefly, I can define like my space V as follows. This is the set of all k prime vectors in n to the n, such that each of the entries of the k prime is less or equal than the entries of k, the original vector that I started with. Then I also demand that a times k prime must be greater than 0, and also like there are some extra properties that regard like the modular space of instance. So I'm just saying here is not P1, not P2. So these properties tell me that if I find something like this, 1 with G loops, this is actually equivalent to only 1. Whereas this tells me if I find 1 attached to an AD shaped quiver with the labels given by the affine linking of that AD, then this is actually equivalent to just having the AD alone. So on this set, now I build some multisets LM. These are multisets of K prime vectors, K prime 1 up to K prime M, such that the sum of all the K prime is less than K. And this M now, it's unique. So if I take an element L inside of like L equal union where M, now this element has a unique M that can be assigned with. And so this M, it's what I will call the length. length.
I don't understand. What do you mean by P1 and P2? You said not P1, not P2. What does it mean?
That if you get here this vector k, which is just suppose it is 0, 1, because I started with a quiver with twins.
Yeah.
And then the matrix is of this form, is -2, and here I have 1, 1, and here I have +6, for instance. Because these would mean that I have 4g, g will equal to 4.
G is 4. Okay.
Okay. When I do this, like on the first line, I will get.
This is negative, the Cartan matrix you're using.
Yeah,
Okay.
I would get a 1, and over here I will get a 6 as a result. But this result must be taught as equal to just having a -2 instead of the 6. Okay, and so the total here will just be like.
I just don't understand what you mean by not P1, not P2. You're looking at the set of all K prime less than or equal to K satisfying some property, but not P1 and not P2. Does it mean K prime can't equal P1 or K prime can't equal P2? I don't know what P1 and P2 are.
Modulo of K prime is equal to 1. Then I demand that A K prime transpose, this guy should be actually greater than 0 and equivalent to the case where G. I make now an equivalent statement with a tilde, which is the same as A, but I substitute like the G with 0. What's P1 and P2 are? The modulus space of instants. So if I take U1, P1
space of instant terms is not the P1 and not the P2.
exactly. So P1, the thing is that
Moduli space of instant terms is not the P1 and not the P2.
yes,
Whenever you mention moduli space of instant terms, then you mention P1 and P2.
P1 is telling me that I need to consider U1 with G adjoints as the same as a U1.
Well, what?
Where is the P1? What do you call it the P1?
This is my P1 property. That I do it
P stands for property.
property.
Okay.
Is no property 1 and not property
Not
2.
property
That's
1.
That's what.
Okay.
Well, I'm not.
Okay. So sorry.
But, so this is a condition on the K
Yes.
prime,
Yes.
but I don't understand how a condition on the K prime can be that you consider loops to be the same as no loops. What does that have to do with a condition on K prime?
I'm constructing now a set of.
Yeah, I understand you're
good K
constructing a
prime.
set of K prime,
A
but
good
so
K
what
prime
K
that
prime
can-
is not good? What K prime would be not good here?
So the K prime that will not be good would be as follows. If I have 1
With
and then
loops,
1 over here,
right?
so
That's
you
not
would say that if you do this multiplication with the vector 0, 1, it's good. It's the example that I gave you before with the matrix, no? Because you have -2 plus G, then you have 1, 1, and then -2. I multiply it by this, and then I get as a result 0 and -2. No, sorry, 1 and -2 plus G. Now, this guy, since K should be in N, you would tell me, if I take G that is greater than 1, this thing is okay. Like I don't care. This is positive. But what I'm telling you is that actually this guy is not okay. So this G is negative. Is like this entry should be negative. So it's the same as G were to be 0. So this, which would not be allowed. So this is what not P1 is telling me. That if I encounter a case where I have a vector with modulo 1 that multiplied like this gives me like this minus 2G,
So you're saying
minus
that,
2 plus 2G.
you're saying that 0, 1 is not good here. Is that what you're saying?
Exactly. So that's one.
0, 1, you're saying is not good.
It's not
Because even though you have a loop at the 1 to make this something that should be good,
yes.
you want to throw away the loop. So not P1 means that it should still have the property A K prime bigger than 0 when you get rid of the G.
Exactly.
So why not just say,
Because this applies-
why not just use the matrix without the G's?
Because this it's valid only if the modulo of K is equal to 1. If I put a 2,
Well, only for an elementary
Exactly.
vector, you want to exclude all, so you just want to exclude all elementary vectors. P1 means
yes, exactly.
every elementary vector is excluded.
Exactly. If I put a 2, then it's fine. It's perfect.
And P2 says what about the,
P2
we do
says
not want to allow,
That
we do not want
if
to
we have
allow.
this, no, it's other. This one says that if I have this, like, for instance, this
Mhm,
is a finding in of A3
mhm.
with levels multiplied by n attached to a 1.
You don't want that either.
This one, I'm saying that should actually be regarded as this guy. So I need to throw away the 1. So I'm considering all the set of
So
K.
you're just saying you want an imaginary root in this, that's sigma 0, I guess. Sounds like.
Right. Fine.
In the fundamental domain. Okay.
Do
Fine.
you have some such photo?
Yeah, Coley-Bovey defines something that I think is the same as this a long time ago.
What could they like?
Well, yeah, I mean, the first criterion says that you're not a real root. So you're looking at the only things in this set sigma 0, which have simple representation. First thing says you're not a real root. And the second one is, well, it's eliminating something which is not in this set sigma. Because if you, in this particular case of this 1, but the m times the Dinkin thing, this actually decomposes as 1 plus and with the other one. So it's not in this set sigma 0. This is one of these exceptions to
Actually, the same theory is exactly the same procedure as we do to find the local description of the closure on this.
yeah, there's actually another condition that also, right, that he would have there. Like, in the Crowley-Bovey picture, you would have, if you have something which has 2 1s attached to each other,
Yeah.
then you can split them.
So something like
If you have anything, and then you have a 1
1
attached by 1 to a 1, and then anything else attached to the
Works
first one, yeah,
right.
exactly, then you would split these into the sum of the 2, exactly. They wouldn't include that in your set either. If it's this sigma.
And just one link between the.
Yeah, just one, yeah, that's important.
But you're keeping the 1s or you're eliminating the 1s as a number?
Yeah, you split it, you keep the 1, q prime
You keep
attached
the
to the
ones.
1. And the q double prime attached to the 1, yeah.
This is allowed if for me like these 2 1s like have greater than 0 value. So yes, I can do this, but this is already inside of this.
No, I'm saying that the set Coley-Bovey defined this first thing, when they're attached, would not be in the set. You would instead use the split it and look at those 2 things in the set.
No, for us, this will be 2 different things.
Those are both in there. Okay, so
Yeah,
it's not
those are
exactly,
both in there, but they're different for the fact that if I compute the Coulomb branch dimension of this guy, the
Mhm.
Coulomb branch dimension is Coulomb branch of Q prime plus Q plus 2 minus
Right.
1. Whereas here is Coulomb branch of Q prime plus 1 minus 1. And then Coulomb branch of this plus this minus 1.
Okay,
So,
okay.
Yeah, you need another one on the, no,
yeah, exactly.
the Q1 goes to 2 and then to 1. You end up with 2 nodes of 1 on the row apart.
I have two. One is here and the other one is here.
No,
I'm sorry.
add another one.
Well,
Add to the 2 on the first one, just extend it. The node that you split,
yeah,
it's a, no. No, the
I split it
one
like this.
becomes 2 nodes. No,
In the Higgs branch picture, it's
No,
the same.
no, because every Coulomb branch has to have a framing. So you frame it on the 1,
and then you pull the quivers apart, and then you can put the friend.
No, but what you're doing, I understand what you mean. You say you engage on these guys.
No, no, I'm engaged on the one.
On the one. Let's make it bigger.
That's all.
You want to say, I start with this one, Q prime and Q.
Yeah.
Then you engage on
either one.
on either ones, for instance, this.
Yeah.
And then what you can write down is that here you
Put a
have,
square.
this is a square, and
And
this
then-
is one thing,
Yeah,
and then
put the square on the other one. That's it.
that's it.
There you go.
But this,
And then you can put the one somewhere else if you like, or two pieces on frame.
but this is not what Travis was saying. Travis was saying that you, like if I understood correct, he was saying that for him, this guy should have been identified with the following. With the following one. Which for us,
Well, that's not how.
except for us, this is not an identification, but this is a fission process. So it's allowed for decay and fission. I'm now not saying that these two are equal, but this is an X.
Yes, yes.
Yeah, so it's a different.
You had to know the other one, and then you basically gauge the way.
Yeah. That's
The point is that what we do is an algorithm which works well. And one has to understand why this determines this algorithm and not the
for us, I mean, like our perspective is either like their move is what Rudolph was mentioning of engaging one of the three ones, and then it's perfectly fine, like we have it like recovered 100%. But if we're talking about like if this algorithm that they're mentioning gives you Xing, then we need to see whether that's an equivalence relation or it's an Xing process. Because if it's an Xing, it's fine. If it's an equivalence relation, we're not fine. Because for us, these two things are different.
Yeah, the Google branches are different.
Yeah.
But the heat branch is maybe the same.
No, the heat branch is not.
Because the free field piece of it,
Yeah.
goes evaporates. You know, the one added on to the end of the quivers.
I agree.
Where
I agree. But problem is that now we're looking at Coulomb branches.
We're looking at Coulomb branches. Maybe call those your own words for things.
For X branch.
is the only considered.
Yeah, but always case is to the heat branch also.
In this case,
Yeah.
theoretically, why?
We just took the example like the Q and Q prime, just like they were two, and then it's here. Yeah.
But maybe it comes with the fact that I'm considering unframed.
But yeah, then we can discuss it.
But I would say, I mean, we're already past the hour, so. if
Yeah, we should probably get lunch. People probably want to get lunch.
It's very important to check the algorithm, to check for the discrepancy, and to understand why this discrepancy.
Yeah, maybe during lunch, like we can discuss a little bit about this, like the math part of the algorithm. Like what does it mean? But, yeah. Shall we stop here?
Well, we can get lunch and then we can still come back and try to understand it better. All right. Thank you.
Then let's just close it on.
Because we got into this long discussion about this set V, but actually
Yes.
you wanted,
I've yet to
you wanted to
use
tell
the
us
set
something
V.
about this set V, so what did you want to say about this set V?
So what I wanted to say is that once I construct this set V that has these properties,
Right.
I can build a multiset with elements of V such that this LM, if you take the elements of the multiset, you sum the entries, then this should be less than K.
Okay,
And now I can construct a space just by L, capital L, as a union of all these sets. Now, the thing is that I constructed this because I wanted to have.
sorry, I'm recording this.
The thing is
Okay.
that I wanted to have a partial ordering
Mm-hmm.
on this set of case. And I'm close to be there. So the idea is that instead of looking only at V, I
Mhm.
look at elements L, which can be elements of this multiset. And this uniquely defines an M. So this L, it's within L union on all games. This M, it's unique.
M is the length.
Yes.
And
I
what
call
this
it
says length?
Length of L.
Okay.
So the thing is that now I want to give a notion of order that leverages on my definition of length. So I can say that two elements, so two quivers, L1 and L2 are separated by an elementary transition. So there is just one transversal slice between the two. If L1 goes to L2,
So can I make sure that his Ki prime is in the set V or what does it mean inside of K?
this is less.
Less than K,
Yeah, so you just sum the entries. If
should be
you-
less than the K. Ah,
Yes.
okay.
Less than the entry of K.
Ah, that's it. No condition on it.
No condition on it. This one is free because all the conditions like you put them in B with all these properties.
Mm-hmm.
So once you have the condition free, then you just get this.
But they didn't say that the K prime had to be in V though.
K prime.
But that K prime,
Yeah, sorry. K prime. For me, K prime and load is the
V, okay, all right, sure. So some kind of decompositions.
Excel.
Exactly, yes, okay, so this is very reminiscent of what happens on the Higgs side.
Where I want to say that the theory L1 exists to the theory L2 if the difference in length, the modulo, so this would be length.
Actually, it goes back to comment by what
Mhm.
it said that these angle things. This first.
Oh, yeah.
You say that you're using very similar algorithms, one for this one for food.
Right,
But they are very close with the.
true.
So one difference in length is less than one, and the intersection of these two elements is actually length of L1 minus one. And obviously, like the sum of the elements in L1 must be less than the sum of elements in L2. Then there is a flow. We say that there is a flow between L1 and L2, and so L2 is smaller than L1. So let's make a practical application so that we're all on the same ground. So if we take, for instance, the following figure, 4, 2, 2.
And I have a little problem here. The length is an integer, right?
The length is integer.
So if
Yes.
the difference is absolutely less than one, it just means the difference is zero.
Sorry, it's equal to 1.
Oh,
My
okay,
fault, but yeah, you're right.
okay.
No, actually, you can also get
Less than or equal,
this
you
is
want?
actually, I mean it that it can be either equal to 1 or 0.
Right, so less than or equal to one would have been okay.
That's
Just
why
you
I
wrote less than.
Yes.
Okay, less than or equal to one. And then the intersection is exactly one. So they could be the same size, but they intersect along all but one of their elements, or the one of them can be a subset of the other.
So
Or they
you would
can
see
be-
this explicitly from, no, I take this figure, this is the modular space of two different.
Hmm.
If you compute the block branch, that's what you get. Now, thing is, since
It's not precisely.
L2 can't be bigger than L1. L2 could be either the same size as L1 or L2 could be one less. So actually you don't need the absolute value. It's actually without absolute value, it's true.
so
Now what failing.
yes, but we allowed for the property the one and the not P2, the difference of these, which gives me a framing. Now I need to consider it equivalent to the one without. So that's why I'm saying this is modular space. modulo this. Now the thing is, the quiver can fission, the reason why fission, so the length now changes. I fission it into two quivers. Two,
I guess
one,
L1 could be smaller than L2 as well.
yeah,
That could also work. Okay.
two, one, 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 one. Now you can see that the sum, the limit is actually equal. But then if I compute the length, this is length 2 and this is length 1. And when I'm doing this is the fission, and this is just an A1 transition. Then I can kill.
So these are the things you're drawing, L1 and L2, or? No,
This is a yes, this is my.
I don't know what the thing, how the diagrams correspond to L1 and L2.
So suppose that this is my L1.
This is L1, okay?
Now L1 is defined by the vector 2, 2, 2, 2, 4.
Mm-hmm.
And the adjacency matrix follows this. Now I think L2 is given by the vector 1, 1, 1, 2 and 1, 1, 1, 1. So if I sum the elements, you can see that there is an order. If I compute the length, this is length 1, because this is inside of.
This is m equals to 1. L1 has m equal to 1, and L2 has m equals to 2. You
Yes.
see.
So
Ah,
the difference is 1. And
L2 has m equal to 2. And now, but in order for this to work, the intersection has to be 0. That's true, though. They don't intersect at all.
yes.
So this would be included, yeah. Okay.
So there is we say that there is a flow from this theory to this one. So this is the modular space of two different instantons, and this one, they are singularly one different instantons, but since they come from this, they're indistinguishable. So it's what we will write down. Maybe I go in this direction. This. I can kill one instanton. And since I have two of them, which are equivalent, I put 2.
Right.
2, 1, 1, 1, 1. And now I have just one instanton that I can kill, and it goes to 2. So if I consider in fact the Coulomb branch, this guy, the Coulomb branch of this guy is exactly this symplectic similarity, the one that has A1 to D4, D4. If I consider the Coulomb branch of this guy, these are just 2 D4 copies that are intersecting at the origin.
Mhm.
And in fact, like you can see from
I
this.
see.
Whereas if I consider the Coulomb branch of this is just a minimal equivalent orbit of a solid. And
Mhm.
so that's it. The idea is that you can now take whichever quiver shape you want and run this algorithm. You will produce a lot of quivers, and those quivers will give you the foliation.
Mhm. It seems like it's not. Like you could have replaced this L1 with something quite different in the L2. Like any collection of two things, neither of which was the one on the bottom, would satisfy these conditions
Yeah.
you wrote here. So that's quite non-restrictive, but
So
you could have increased these dimensions on the L2, and this would still have satisfied the conditions you wrote down.
no, but you will have the problem here with the sum of the elements.
It'll
If
still
you
be less
increase-
than, or if you increase the L2s, it'll still be satisfied. This less than or equal will still be satisfied.
How do you want to increase it as an example?
Like if you place it instead of 2, you put 3 or whatever on each
No,
of them.
but if you put 3, now let's suppose that you put 3 over here. Then this means that this vector became 3. And so if you sum this, you get a 5. 5 is bigger than 4, so this relation is not equal. It's not
It is
satisfied.
satisfied. You said L1 is less than or equal.
I switched,
Ah,
I switched them. 2. And before they were equal, so it was 5. Now, in fact, it's L1 flowing to L2. So L1 is the dominant. It's dominant.
okay, but
Okay. Now, so let's go back.
but it could be much less, right? You could like throw away most of the diagram and
Yes.
just have 2 things somewhere, and that would be allowed here.
Yes, but the problem is that we're taking elements in D. So
Right,
if you throw away more stuff, suppose that you want to throw away these. And so I have the 0, 0, 1, 2.
Mhm.
Now, if you have this vector and you try to.
Yeah, it may not be in V in general, that's true.
Hey, that's not easy.
But you could have a pretty big quiver you start with, and you have a big L1, and then you could have just two tiny little pieces of L2, and that would always be allowed under your rule.
Yes, and this would be efficient because you're taking your code, you're splitting it in half.
But they don't add up, they don't have to add up to the whole thing, they can add up to
Yeah.
some very small piece of the whole thing.
These are the logical.
Oh, yeah, yeah, I think we have to go.
Because strictly speaking, we have to. What we, the
Yeah. Let's go in.
because